2004 grade 11 Hypatia math contest. Find all values of x which are the roots of that equation. Okay, well, I believe it factors into x plus 3 and plus 2. So therefore the roots are x equals minus 3 and x equals minus 2. Part B. The roots of that equation are increased by 7. Find a quadratic equation that has these roots. Okay, so the roots are going to be increased by 7. So minus 3 plus 7, that's 4, right? Yeah. And then the other root, minus 2, is increased by 7 to get 5. So these are the two new roots here. So that means the equation would basically be x minus 4 times x minus 5 equals 0, I guess. And then if you expand it, it would be x squared minus 9x plus 20 is equal to 0. Part C. The roots of this equation are increased by 1. Find an equation that has these new numbers as roots. Okay, so first thing we have to do is figure out what are the roots for this equation. And let's factor this guy here. So let's see, I think that would be 3x, x, 2 and 1, and then plus minus, I believe. That would be the factors. Yeah. So that means these roots are x equals 4, x equals minus 2 over 3, and x equals 1. So they're saying that these roots are now increased by 1. So 4 plus 1, so that root becomes 5. Minus 2 over 3 plus 1, so that becomes 1/3. And then 1 plus 1, which becomes 2. So these are the new roots. And then we have to make an equation with those. Okay, not a problem. So that's going to be x minus 5, this first root. And then x minus 1/3. And then x minus 2 is equal to 0. So if you expand this, I guess I'll let you do that, right? And then when you expand it, you get x cubed minus 22 over 3, x squared plus 37 over 3, x minus 10 over 3. And then what I did is I multiplied through by 3 to get rid of all the fractions. So I've ended up with 3x cubed minus 22, x squared plus 37, x minus 10 is equal to 0. And that's perfectly valid. Two basketball players, Alan and Bobby, are standing on level ground near a lamppost which is 8 meters tall. Each of the two players casts a shadow on the ground. On the diagram, Alan is standing 2 meters from the lamppost. If Alan is 2 meters tall, determine the value of x, the length of his shadow. Okay, so this is one of those similar triangles situations. I don't know if you can actually read these. Let's label it properly. 8, 2, 2, and x. So these are similar triangles, these guys. So that basically means that 2 over x is equivalent to 8 over 2 plus x. And that's it. That's basically how you would solve it. So cross multiply and you get 4 plus 2x is equal to 8x. 4 is equal to 6x, and therefore that would be x is equal to 2 over 3. And that's it for part A. Now we have part B. Bobby is 1.5 meters tall and is standing on the opposite side of the lamppost from Alan. How far from the lamppost should she stand? Oh, Bobby's a girl. So that she casts a shadow of length 3 meters. Okay. So this scenario is not going to be drawn to scale, but you guys understand. So here's Alan, here's the lamppost, and Bobby is about here. So it's one of those situations. This is Bobby. Okay, so let's label this now. This is 1.5. This is a standard 8. And how far should so the length of the shadow is 3. So this is going to be 3, and then this is x right here. Okay, so same story. 1.5 over 3 is the equivalent of 8 over 3 plus x. Right? Okay, I think that's it. Cross multiply and you get 24. And then you get 1.5 times this guy, which would be 4.5 plus 1.5x. And then therefore this would be 19.5 is equal to 1.5x. And therefore x is equal to 19.5 divided by 1.5, which is 13. And 13 is the answer. In the diagram, triangle OMN has vertices 0, 0, 6, 0, 0, 8. Determine the coordinates of point P, A, B inside the triangle so that the areas of the triangles POM, PON, and PMN are equal. Okay, so again, I don't know if you can read this, but this is the origin 0, 0, 0, which they've called O. This point is M, which is 6, 0. This point is P, which is A, B coordinates. And this point over here is N, which is 0, 8. And they're saying that they want you to figure out what are the coordinates so that three triangles have equal area. And those three triangles are triangle POM, triangle PON, and triangle PMN. Okay, well, let's draw some lines here. This one, and I think that's all we need. So the area of triangle PON, 1/2 base times height, POM, right? So 1/2 the base is 6, and the height is B. So this is just 3B. PON, this one would be 1/2 base times height again. The base we can use is 8. The height will be A. So this is just 4A. And then finally, PMN is a little bit different. PMN, we have to take the full area of this whole guy here. So that's going to be 1/2 base times height. So 1/2 6 times 8. And then subtract from it these guys. So 3B minus 4A. So that's basically 24 minus 3B minus 4A. And they're saying that this, and this all have to be equal. Okay, so let's solve for that. Let's just keep this here. Okay, so first of all, 3B has to be equal to 4A. Okay, and then this big long one, 24 minus 3B minus 4A has to be equal to, well, either of them. So let's just set it equal to 4A and try to solve this. Okay, well, 3B, I can just substitute that. So 24 minus 4A minus 4A is equal to 4A. Okay, put all the A's on one side, and we get 12A, and therefore A is 2. And then substitute that into there, so 3B would be equal to 4 times 2, so B would be equal to 8 over 3. Okay, so therefore that point P is 2, 8 over 3. All right. Now we move on to part B. Okay. In the diagram, quadrilateral OMLK has vertices 0, 0, 6 zeros, 10T, and 0T, where T is greater than 0. Show that there is no point QCD inside the quadrilateral so that the areas of the triangles are all equal. Okay, so the same story, but this time a little bit different. So we have triangle QOM, which is, well, I'll figure it out a little bit later. Then we have triangle QLK, triangle QKO, and finally triangle QML. All right. So I don't want to make the diagram too messy, but I'm just going to draw a few lines. This line, this line, this line, and one final line that goes down that way. Okay, So QOM, I don't know if you can even read this, but this is O, this is my M, this is, what is this? L up here, and this is K. And then Q is here, what it's pointing to in the center. Okay, so let's figure this out. QOM is going to be 1/2 base times height. The base, well, let me write in the coordinates since you probably can't read them. The diagram is not very nice here. 0t and 10t. Okay. And then Q is C and D in terms of its coordinates. All right, here we go. So 1/2 base times height. So we got 1/2. The base would be 6, and then the height would be D. So this is 3D. All right, next one, QLK. 1/2 base, we will put 10. And it's going to be, let's see, T minus D, right? Yeah. So that's 5T minus D, like that. QKO. QKO. And that's going to be 1/2 base. So the base is T. And then the height is going to be C. So this is basically TC over 2. QML is a little bit more complicated. QML is going to be the entire quadrilateral minus 1, 2, 3, 4 triangles. So actually the entire rectangle, I should have said. Sorry, rectangle. The rectangle is a 10 by 6 rectangle. Oh, sorry, not a 10 by 6, a 10 by T rectangle. And then we have to subtract. First we have to subtract this guy. So that's going to be 1/2 4, I believe, times the height, which is T. And then I just have to subtract this guy, and this guy. So minus 3D. Minus 3D. Minus 5T minus D minus TC over 2. Got it? Okay, so let's simplify this a little bit. This is 10T minus 2T minus 3D minus 5T plus 5D minus TC over 2. Any more simplification? This and this and this, so 8 minus 5, so that's that 3t. Yeah, 3t. And then this and this will plus 2d. And then this minus tc over 2. Okay, that's about as far as I can go. Okay, so now at this point we got to figure out what to do here. Oh boy. So let's just put this here, QML. So all of these they want to be equal, but they're saying that show that there is no such point. So eventually you're going to get a contradiction. Okay, so let's see what we can do here. Well, let's just work with this one and this one first. So if we have 3D is equal to 5t minus d, right? They all have to be equal. So 3d is equal to 5t minus 5d. So that means that 8d is equal to 5t, right? Okay, so that means that either 8d over 5 is equal to t, or it means that d is equal to 5 over 8t. Those are the possibilities. Okay, great. So far, so good. Now let's turn our attention to that guy, tc over 2, and it's going to equal any of those, so let's just make it equal 3d. And then what can I substitute here? I can substitute the fact that t, this t is equal to 8d over 5, and then we'll have just c over 2, 3d, and then the d's will cancel. Okay, that's good. So that would mean that c is equal to 3 times 10 over 8, which is 30 over 8, which is 15 over 4. Okay, so I got a numerical value for C. That's pretty good. I don't know how that helps me, but so far so good. And then now, what can I do here? I guess I can plug them all into the big long one. So this one, and let's just use this one. So 3D is equal to 3t plus 2d minus tc over 2. Yeah? Okay, let's see what we get. So I'm going to break this up into left side and right side, and let's see what happens. So left side, and I'll try to put it in the same variable. So let's use t as the same variable. So 3d is the equivalent of 3 times 5 over 8t. So that's going to be 15 over 8t. Right? If I did this properly. I was 3d, right? And then d is equal to, right here, 5 over 8t. So that's how I got that 15 over 8. Okay, let's keep going. So the right side is going to be 3t plus 2d. So d, again I'm going to substitute that 5 over 8t minus t. And then c is a numerical value 15 over 4. So let's see here, we have 3t plus, this is a multiplication, so that's 10 over 8t minus 15 over 8t. So let's just get a common denominator, top and bottom by 8. So 24 plus 10 minus 15 all over 8t. And that's going to be 34 minus 15. So that's 19, right? 19? Yeah, I think so. I don't think I made any mistakes. So that's going to be 19 over 8t. So left side is 15 over 8t, and right side is 19 over 8t. So left side does not equal right side, so we have a contradiction. And therefore you can conclude what they're saying, that there is no indeed such point that can make this all work. One green, one yellow, and 2 red balls are placed in a bag. 2 balls of different colors are selected at random. These 2 balls are then removed and replaced with 1 ball of the 3rd color. This process continues until there is only 1 ball left in the bag, or all of the balls are the same color. What is the color of the ball or the balls that remain at the end? So let's start. We have green, we have yellow, and we have 2 red. So we are going to remove, and then we are going to have what is remaining. So let's figure out some scenarios. If you remove green and yellow, you have RR remaining. But according to the question, we have to also add one of what was not removed. So we removed a green and a yellow, so the other color was red, so that's what we have to add. So we have to add a red. So there you go. We immediately arrived at a situation where all the balls are the same color, and that color is red. Now, of course, this is not the only scenario. We have a couple more scenarios. The other scenario is that if you initially removed a green and a red, if that's the case, then you would have yellow and red remaining. And then you have to add what you didn't remove. You didn't remove the yellow, so you have to add a yellow. But then we have to continue now. Now, we can only remove a yellow and a red. That would leave a yellow. But then we have to add to that green, because green was something we did not remove. And then now we can only remove a yellow and a green, and then we have to add what we did not remove, which was a red. So in this scenario, we end up with red as well, because this is now only 1 ball left in the bag. because it's that or that. And then the final scenario is if we started by removing yellow and red. If we do, we have remaining green and red, and then we have to add to it the color we did not remove, which was green. So we have a GR scenario. Now we can only remove green or red, and when we do, we have just one green left. We have to add a yellow, and then we can only remove the green and the yellow, and when we do, we have to add the color we did not remove, which was red, and there you go. You get right back to having a red. So in all three scenarios, we end up with red. So the answer to this question is red. Three green, 4 yellow, and 5 red balls are placed in a bag. If a procedure identical to that in part A is carried out, what is the color of the ball or balls that remain at the end? Okay, so we have green, green, green. Let's do it on the side here. Let's do it over here. So we have green, 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 yellow, 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 and then 5 of these reds. And then same story, and let's see what we get at the end. Now, I'm just going to do one scenario, and they're saying that, I guess they're saying that there's only one outcome, one color, no matter what the process is. So let's see what color I get. Okay, so let's start. I don't know, I'll remove and then remaining, right? Okay. All right, so I'll start off by removing a green and yellow. So if that's the case, what's remaining is green, green, yellow, 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 and then all 5 of the reds are still there. But then we have to add something I didn't remove, and I didn't remove a red, so I have to add that. Got it? Let's remove again a green and a yellow. So then I have green, 2 yellows, and then I have all 6 of these reds. Now again, I have to add the color I did not remove, which is red. So there we go. Then again, I'm going to just make it straightforward, green and yellow again. So now I have only 1 yellow, I have all of these 7 reds, and then I have to add another one because that's the one that I didn't remove over here. Okay, so now let's, well, I don't have much choice now that I can only remove a yellow and a red. So then I'm down to 1, 2, 3, 4, 5, 6, 7. And then I have to add the color I did not remove, which was green. So I have to add a green. Okay, so let me just see here. 7, and yeah. Okay, great. So now I have to figure out what to do next, and not much choice, really. I can only remove a green and a red. Those are the only 2 colors I have. So that means I am going to be with 1, 2, 3, 4, 5, 6 of these reds, but then I have to add a yellow since that was a color I did not remove. Okay, now again, I don't have much choice. I can only remove a yellow and a red, so I'm down to 5 of these reds, and I have to add a green. Again, remove green and red, so now I'm down to 4 reds, and then I have to add a yellow. Remove a yellow and red, now I'm down to 3 reds, and I have to add a green. Remove a green and a red, and now I'm down to 2 reds, and then I have to add a yellow. Remove a yellow and a red, now I'm down to 1 red, I have to remove a green. Remove a green and a red, and I'm down to nothing, but then I have to add a yellow. And this is my final color. And that's it. So I made one such scenario, and in that scenario I showed that my final color is yellow, and you can create whatever scenario you want. Three green, 4 yellow, and 5 red balls are placed in a bag. This time, 2 of the balls of different colors are selected at random, removed, and replaced with 2 balls of the third color. Show that it is impossible for all of the remaining balls to be the same color, no matter how many times this process is repeated. All right. So, since you, in this part C, you're removing 2, and then you're adding 2, the number of balls stays the same. Number of balls stays same, right? Before it was different because before you were removing 2 and adding 1, so the numbers were getting smaller, but this time the numbers are remaining the same. So initially, if we had a green, yellow, and red like numbers, the numbers would be 3, 4, and 5, right, according to the question. So that is a total of 12 balls. So that means at the end, if you want all balls to be the same color, you'd have to have a situation like this. It would eventually get down to 0, 0, and 12, right? This is a situation where all the balls are red. Or you could have a 0, 12, 0 situation, which would mean all balls are yellow, or a 12, 0, 0, which would mean all the balls are green. So let's just concentrate on this because these two guys will be exactly the same in terms of their explanation. Okay, so what we want to do is we want to go from here to here. Is that possible? Well, I don't know. So let's see, but let's do this by working backwards. If you work backwards, I think it'll be easier. So I'm going to start with the end result, which is a 0, 0, 12, which means that all the balls are the same color, and in this particular case, red. And let's see where it goes to, and if it eventually gets to this. If it does, then the answer is yes, but they're saying that that is not possible, so somehow we're never going to get to a 3, 4, 5, and we have to show that. Okay. So how do we get there? Well, the only way to get there for the next step is a 1, 1, 10 scenario, right? Because if you had 1, 1, 10, you remove, let's say, the green and the yellow, and then you'd have to add 2 of the red, and that would bring you to 0, 0, 12. You got it? And you can think about that a little bit if you're not sure. Then how do I get to 1, 1, 10? The only way is 2, 2, 8, right? You remove a green and a yellow. That would bring you down to 1 and 1. And then you'd have to add 2 of the red. That would bring you from 8 to 10. Got it? Okay, now how do we get to 2, 2, 10? 2, 2, 10 can be achieved with the 3, 3, 6. And then it can also be achieved with the 0, 3, 9. The 3 would go down to 2, the 9 would go down to 8, and the 0 would go up to 2. Okay? All right. And then you just keep going like this. And then you're trying to see if eventually I can get to here. So let's see. 0, 3, 9, I can get to from a 1, 4, 7. Or I can get to that from a 1, 1, 10. Oh, this is here. So this looks like a loop. It's like a loop. It just kind of goes back and forth between the same numbers. Okay. Let's see here. 1, 4, 7. 1, 4, 7, I can get to that from a 2, 5, 5. Or from a 2, 2, 8. All right. And a 2, 5, 5 I can get to from a 0, 6, 6. Yeah. And a 0, 6, 6 I can get to from a 1, 4, 7. Okay, so there's a 1, 4, 7 here, so I got another sort of a loop situation. And then 2, 5, 5 I can also get to from a 3, 3, 6 situation. And I think that appeared here, so again we have a loop. And then 3, 6, 6 I can get to from a 4, 4, 4. Or a 7, 4, 1. And then I think 4, 4, 4 I can get to from a 2, 5, 5. So we basically have a bunch of loops here, meaning all of these have already been repeated. You see the 2, 5, 5 is here. So that means these kind of go round in circles. So for example, one such circle, I'll illustrate it for you, is let's say you started with this 4, 4, 4, this guy. it would go to a 3, 3, 6, right? Then you'd go to a 2, 5, 5. Then you go to a 1, 4, 7, and then a 0, 3, 9, and then a 2, 2, 8, and then a 1, 1, 10, and then a 0, 0, 12. And then this 4, 4, 4, you can get to from a 2, 5, 5. And the 2, 5, 5 you can get to from a 0, 6, 6, and so on. Like, I mean, it all kind of goes round and round and loops. But one thing you'll notice is that this 3, 4, 5 is nowhere in this diagram. Nowhere in those loops does this 3, 4, 5 appear. So that pretty much shows, and you can write it out in a sentence, that it's impossible for all the remaining balls to be the same color. Meaning it's impossible to achieve a 0, 0, 12 or a 0, 12, 0 or a 12, 0, 0 starting with a 3, 4, 5.